This journey will uncover the secrets of one of the universe's most captivating phenomena, the black hole. From their initial prediction in theory to their eventual confirmation through observation, these enigmatic objects have long sparked the curiosity of scientists and the public alike. To truly understand what black holes are, and to appreciate their profound importance to astrophysics, we must first examine the nature of gravity itself. Think of gravity as a vast cosmic fabric that warps and bends around any object with mass. In this fabric, black holes represent the most extreme concentrations of matter, creating gravitational wells so deep that absolutely nothing can climb out, not even light itself. This is precisely why they earn their name. They are regions in space from which light never returns, leaving behind what appears to be a perfect void against the backdrop of the cosmos. For astrophysics, the importance of black holes cannot be overstated, as they offer us a unique window into the workings of the universe. They function as natural laboratories, where the laws of physics can be tested under the most extreme conditions imaginable. By investigating their properties, scientists can work to decode the secrets of gravitational relativity and the very structure of spacetime, treating each black hole as a cosmic puzzle that might hold clues to the origins of our universe. A black hole's formation is an event of cataclysmic scale, typically beginning when a star far more massive than our Sun runs out of nuclear fuel. Without the outward pressure from fusion, the star succumbs to its own immense weight and undergoes a complete collapse. This process compresses its core into an infinitely dense point called a singularity, which is enclosed by a boundary known as the event horizon, the ultimate point of no return. Should you ever find yourself approaching this threshold, understand that once you cross it, there is no way back. Beyond their incredible gravitational pull, black holes have other fascinating properties. A key characteristic is their spin, meaning they rotate, and in doing so, they drag the very fabric of spacetime around with them. This rotation has a bizarre effect on the flow of time in their vicinity, warping and distorting it in ways that seem to defy common sense. While it might sound like a concept straight from science fiction, this phenomenon is a real and critical aspect of how the universe operates. Astronomical observations have allowed us to categorize black holes into several distinct types. Stellar black holes are the remnants of single, massive stars. In contrast, supermassive black holes, with masses millions or even billions of times greater than our Sun, reside at the heart of most galaxies. There is also the theoretical possibility of primordial black holes, which could have formed during the very first moments after the Big Bang, each type providing a unique perspective on cosmic history and evolution. However, the existence of black holes presents us with some profound and unsettling questions. What is the ultimate fate of the matter and energy that falls past the event horizon? Does it simply cease to exist? This line of inquiry brings us to the information paradox, a deep contradiction in physics that has challenged scientists for decades. Resolving this puzzle could fundamentally alter our most basic understanding of physical laws. Within the framework of Albert Einstein's general theory of relativity, the existence of black holes is an entirely natural consequence. His theory reimagined gravity not as a simple force, but as the curvature of spacetime caused by mass and energy. Black holes are simply the most extreme manifestation of this curvature, creating points where the known laws of physics are pushed to their absolute limits and behave in very strange ways. It is no surprise that black holes have also become a staple of popular culture, appearing in countless films, television shows, and books that have captivated audiences for generations. Unfortunately, many of these depictions are highly sensationalized and bear little resemblance to scientific fact. To truly appreciate what black holes are, it is essential to distinguish these fictional portrayals from the far more fascinating reality. As we delve deeper into these cosmic enigmas, we are forced to confront their relationship with fundamental concepts like space and time. Some theories even propose that black holes might act as portals to other universes or dimensions, a notion that compels us to contemplate our own existence and our place within the grand tapestry of the cosmos. With every advance in our understanding, new and more profound questions arise, such as whether we could one day harness the immense rotational energy of a black hole. While such ideas might sound fantastical, scientists are giving them serious consideration as they map out the future of space exploration. The study of black holes is an exhilarating expedition filled with constant discovery. Each new observation brings us one step closer to solving the universe's greatest riddles, and serves as a powerful reminder that our quest for knowledge is a journey without end. To understand the appeal of black holes, you might first ask how one of these cosmic wonders actually comes into being. The story begins with the life and death of a truly massive star. Once such a star depletes the fuel for its nuclear reactions, it can no longer support itself against its own powerful gravity. The star then implodes catastrophically, creating a gravitational force so overwhelming that it traps everything, including light. This is the birth of a black hole, a location in space with infinite density and an inescapable pull. It can be tempting to picture a black hole as a cosmic monster, actively hunting and consuming everything in its vicinity. The reality, however, is a physical phenomenon that is easier to comprehend with a simple analogy. Picture a stretched-out trampoline. If you set a heavy bowling ball in the middle, it creates a dip in the surface. A smaller marble rolled nearby will naturally curve and fall toward the bowling ball. In the same way, a black hole is a massive depression in the fabric of spacetime, drawing in anything that ventures too close. The properties of black holes are undeniably captivating, especially when you consider their mass, which spans an incredible spectrum, from just a few times that of our Sun to many millions or even billions of solar masses. All of this immense weight is crushed into a single, infinitesimally small location, referred to as a singularity, a phenomenon that profoundly alters the very fabric of the cosmos around it by warping spacetime. As you venture closer to a black hole, you would experience its gravitational pull intensifying to an extreme degree, bending the path of light and even distorting the flow of time itself. For anyone observing from a safe distance, it would appear as though time for an approaching object decelerates, stretching out infinitely as it nears the event horizon, the ultimate boundary from which no escape is possible. The singularity at the heart of a black hole represents a profound challenge to our current comprehension of the universe, as the established laws of physics appear to completely unravel there. Attempting to describe what occurs at this point is akin to peering into a bottomless abyss. The further you try to see, the more obscure and bewildering the view becomes. Yet, despite our incomplete understanding, these cosmic objects are fundamental to explaining the universe's development. Indeed, without the influence of black holes, the galaxies and star systems that you see today would not possess the familiar structures we observe. This often leads to the question of whether all black holes are the same, and the answer is a definitive no. They are broadly categorized into three distinct types: stellar black holes, supermassive black holes, and the more theoretical primordial black holes. Let's begin with stellar black holes, which are born from the cataclysmic death of a star far more massive than our own Sun. When such a star depletes its nuclear fuel, it collapses and triggers a brilliant explosion known as a supernova. The incredibly dense core left behind, if it has sufficient mass, continues to collapse under its own gravity to create a stellar black hole whose mass can be anywhere from 3 to several dozen times that of the Sun. Next, you have the supermassive black holes, which present an even more compelling narrative, as they are found at the core of almost every major galaxy, our own Milky Way included. These cosmic behemoths can possess a mass equivalent to millions or even billions of suns. Their origin is still debated, with one leading theory proposing they grow over cosmic timescales by consuming smaller black holes and accumulating vast amounts of interstellar matter. Finally, we consider primordial black holes, a truly fascinating concept that suggests these objects could have emerged in the chaotic moments just after the Big Bang. According to this theory, intense fluctuations in the density of the early universe could have caused pockets of matter to collapse directly into black holes of varying sizes. If they exist, these ancient relics could potentially solve enduring mysteries, such as the nature of dark matter. These different classes of black holes can and do interact in dramatic fashion. For instance, stellar black holes can spiral into one another and merge to form a more massive one. Meanwhile, a supermassive black hole at a galactic center can capture and devour smaller ones that stray too close, unleashing an incredible burst of energy that can be detected from millions of light years away. One defining feature shared by all black holes is the event horizon, which acts as an irreversible threshold in spacetime. Once an object crosses this boundary, the gravitational force becomes so overwhelming that nothing, not even light, can achieve escape velocity. From the perspective of that object, space and time would behave in profoundly strange ways as it continues its journey inward. However, for an outside observer watching this event, the object would appear to slow its approach to the event horizon, seeming to hover there, while its image grows dimmer and redder until it completely fades from view. This disparity highlights the profound questions that black holes raise about the fundamental nature of reality and our perception of it. We are left to wonder if anything could exist beyond the event horizon, but the truth is that we simply lack the definitive answers. Scientists are relentlessly pursuing new theories and making fresh observations that may one day illuminate these cosmic enigmas. Each new piece of data gathered in this field unlocks further questions and unveils even greater possibilities. Black holes are not just subjects of intense scientific curiosity. Their study has significant consequences for our broader understanding of the cosmos. They serve as a stark reminder of the boundaries of human knowledge and the vast expanse of what remains to be discovered. In the same way that explorers once navigated uncharted territories on Earth, we now turn our gaze to the heavens, questioning what secrets these dark phenomena conceal. Ultimately, black holes compel us to recognize that the universe is filled with endless opportunities for learning, and that the quest for knowledge is an unending journey. The real question is whether you are prepared to continue this exploration and discover what lies beyond these mysterious cosmic objects. Our capacity to answer rests on our collective drive to comprehend the universe and our own unique position within it. You might wonder, what makes black holes so fundamentally important to astrophysics? The answer is found in how they deepen our comprehension of gravity, the formation of galaxies, and the very evolution of the universe. Investigating their behavior allows us to learn more about the physical laws that command the cosmos, making these objects natural laboratories where relativity and quantum mechanics converge, pushing the limits of our physical understanding. These cosmic phenomena are also central to the quest for answers about the universe's ultimate fate. Black holes could represent the final state of what were once stars, and, by examining them, we might uncover secrets about cosmic expansion and contraction. It's a concept that is both fascinating and unsettling, to imagine a distant future where everything we recognize is consumed by a black hole. It is also worth considering the relationship between black holes and energy. Some theories suggest that matter falling into a black hole isn't truly lost, but is instead converted into energy through extraordinarily complex mechanisms. This idea presents the intriguing prospect that humanity might one day harness this power, effectively turning black holes into boundless sources of fuel. Of course, the very nature of their existence is shrouded in mystery. Although black holes are themselves invisible, you can feel their immense influence through the light of nearby stars, which is warped by their gravitational pull. This presents a unique challenge. How can we possibly study something that cannot be seen directly? The solution lies in observing their effects on their surroundings and by detecting the gravitational waves they emit when they merge. Each type of black hole offers its own unique story and set of properties, making the field endlessly captivating for astrophysicists. From the smallest primordial black holes to the gargantuan supermassive ones at the hearts of galaxies, every one of them has a distinct part to play on the cosmic stage. As our exploration of space continues, they will surely remain one of our greatest puzzles, compelling us ever onward. Black holes, with all their variety and defining features, are far more than just compelling oddities. They are essential to grasping how our universe operates. They demonstrate that there is much more to reality than what we can perceive with our senses, and that even in their destructive power, they can serve as fountains of energy and knowledge, making their study one of the most thrilling frontiers in modern science. When Albert Einstein introduced his general theory of relativity in 1915, it accomplished something far greater than simply changing our view of gravity. It gave us a glimpse into a cosmos of unimaginable complexity. Have you ever considered how a truly massive object, like a star, can actually bend the fabric of spacetime that surrounds it? Grasping this concept is absolutely key to understanding black holes. According to Einstein's theory, gravity isn't some invisible force that pulls objects together. Instead, it is the direct consequence of mass causing spacetime to curve. You can picture spacetime as a gigantic, stretched-out rubber sheet. If you set a heavy bowling ball on it, the sheet will dip and form a well. A marble rolled nearby will then travel toward the ball, not from a direct pull, but because it's following the curve in the sheet created by the larger mass. So, what unfolds when an enormous star depletes its nuclear fuel and collapses under its own weight? This process can be so violent that the star becomes a black hole, a point where spacetime's curvature is so extreme that nothing, not even light itself, can break free. This leads to a logical question. If light cannot escape, how can we be certain that black holes are real? The proof is found in the indirect clues they leave behind, such as when a star is observed orbiting what appears to be a massive but invisible companion. General relativity also introduces the critical concept of the event horizon, which you can think of as the black hole's ultimate boundary, its point of no return. Imagine a river with a current that grows so powerful at a certain point that no boat could ever turn back. The event horizon is precisely that threshold in space. Anything that crosses this line is irretrievably pulled into the black hole's depths. Einstein's theory also illuminates how time itself behaves in the vicinity of a black hole. Have you ever noticed how your perception of time can seem to speed up or slow down? A similar but very real effect occurs in the spacetime near a black hole. For an observer watching from a safe distance, time, for an object approaching the event horizon, would appear to grind almost to a halt, which prompts the speculative question of whether one could travel through time near these cosmic giants. As we delve deeper into general relativity, we also learn about the existence of spinning black holes. These objects don't just pull matter in, Their rotation actively stirs the spacetime around them. Much like a whirlpool drags everything nearby into its swirling currents, a rotating black hole can drag the fabric of spacetime, creating a region known as the ergosphere, where matter and energy can be powerfully influenced and, theoretically, even extracted. Ultimately, general relativity is more than a fascinating scientific theory. It poses deep philosophical questions about the very fabric of our universe. If gravity possesses the power to bend both space and time, it forces us to reconsider our entire perception of reality. The notion that space and time are not fixed, but are instead malleable, opens our minds to the limitless possibilities that the cosmos may hold. Among the most compelling and perplexing objects in the cosmos are rotating black holes, but you might wonder what exactly makes them so remarkable. To begin, it's crucial to recognize that black holes are not all identical. Much like the variety you see in stars and planets, there are distinct categories of black holes, and those that spin possess singular properties that distinguish them from their static, non-rotating relatives. To help you visualize this, think of a powerful tornado. The force and spin of the vortex draw in the surrounding air, resulting in a phenomenon vastly different from a calm body of water. Similarly, a black hole that rotates operates differently because of its spin, a motion that impacts not only its internal structure, but also the very space surrounding it. This spin causes the fabric of our universe, known as spacetime, to be warped in a unique way, as if the black hole itself is dragging the cosmos along with it in a massive whirlpool. This distortion is more than a mere visual curiosity. It carries tangible consequences for how matter and energy behave in its vicinity. For rotating black holes, this dynamic introduces a fascinating region called the ergosphere. This area exists just outside the event horizon, the ultimate point of no return, and is where the black hole's spin dominates everything nearby. Within this zone, any object that gets close enough not only experiences the immense gravitational pull, but is also irresistibly swept up in the black hole's rotation. The ergosphere is a domain where space and time merge in bewildering ways, resembling a turbulent ocean with perpetual waves driven by an unending vortex. So, what occurs when an object ventures into the ergosphere? Unlike the situation with a static black hole, where falling past the event horizon is the only possibility, the ergosphere offers a chance to actually gain energy and be flung back out into space. This process is called energy extraction from the ergosphere. You could compare it to surfing. If you successfully catch the right wave, you can ride its momentum to the shore instead of being dragged out to sea. While a simple comparison, it helps illustrate how an object can harness the immense power of a spinning black hole for its own benefit. This concept of drawing energy from the ergosphere is not just a theoretical exercise. Scientists have already conceived of methods to potentially harness this power in the future. Should we ever create the technology to reach this region, we might be able to tap into energy sources in a manner that currently seems confined to science fiction. You can only imagine the implications for our civilization, from accessing nearly limitless power that could revolutionize our existence to transforming our ability to explore the universe. When considering the spin of a black hole, it is also essential to note its influence on gravity in the local environment. The rotation does more than just warp space. It can also alter the behavior of nearby matter. Stars and gas clouds orbiting a spinning black hole, for instance, might be subjected to forces they wouldn't encounter near a non-rotating one. In this way, a rotating black hole acts like a cosmic manipulator, not just luring in matter, but actively meddling with the laws of physics in its immediate neighborhood. To grasp these phenomena, you must turn to Einstein's general theory of relativity. This framework reveals that gravity isn't merely a force, but is the curvature of spacetime created by mass. A spinning black hole, with its incredible density and rapid motion, therefore warps its surroundings in ways that defy easy imagination. To simplify this without complex mathematics, you can picture a taut bedsheet. Placing a heavy ball in its center causes the sheet to dip. Now, if you spin that ball, you'll observe that the fabric not only sags but also twists, forming a vortex. This straightforward analogy gives you a clearer understanding of how a rotating black hole can manipulate the space around it. The deeper we investigate the mysteries of rotating black holes, the more captivating questions emerge. What might happen if a starship managed to get close to the ergosphere? Is it possible that humanity, in a not-too-distant future, could learn to navigate these cosmic currents? While science fiction has long explored such ideas, the real-world obstacles are staggering. Yet human curiosity remains a relentless force, and each discovery we make about black holes invariably leads to even more profound questions. Ultimately, rotating black holes are far more than simple celestial objects. They serve as portals to a universe where the fundamental principles of physics are stretched to their absolute limits. The nature of their spin, the energy they can unleash, and the profound influence they have on their environment are all facets that continue to test the boundaries of our comprehension. As our exploration persists, an incredible future opens up before us, rich with possibilities where the cosmos's greatest secrets might be far more accessible than we currently believe. The event horizon of a black hole stands as one of the most enthralling and cryptic ideas in all of astrophysics. But what is the true meaning behind this term? To comprehend it, you must first envision an environment of utter extremity. Imagine a location where gravity has become so overwhelmingly powerful that absolutely nothing, not even light itself, can break free. That location is the event horizon, a definitive boundary that divides our known reality from a complete unknown. This concept of a threshold from which there is no return is deeply unsettling, because if you ever cross that line, you can never go back. In the end, Einstein's general theory of relativity doesn't just give us the framework for understanding black holes. It also challenges our very perception of reality. The manner in which these colossal, almost mythical objects manipulate spacetime forces you to reconsider the fundamental fabric of the cosmos. As we venture further into these cosmic enigmas, we find ourselves standing at the precipice between the known and the unknown, where our innate curiosity propels us toward new and exhilarating frontiers of knowledge. As you draw closer, the gravitational pull strengthens, causing time itself to act in peculiar ways. To an external observer, time seems to decelerate for any object approaching this threshold. If you were to watch someone fall toward a black hole, their movement would appear to slow dramatically as they neared the event horizon, eventually looking almost frozen, a visual distortion produced by extreme gravity. Once you cross the event horizon, you are instantly transported into a completely different reality. Any light trying to escape is bent and warped by the immense gravitational forces, giving rise to a phenomenon called gravitational lensing. This effect not only curves the path of light, but also fundamentally changes your perception of space, making objects appear nearer than they are, and causing your field of view to shift unpredictably. Imagine the sheer confusion of attempting to find your way in a place governed by entirely different rules of space and time. This brings us to one of the most profound questions. What exactly is inside the event horizon? The honest answer is that we simply don't know, as our current understanding of physics completely breaks down at this point. Some scientists theorize that a black hole's core, known as the singularity, is a point where all its mass is compressed into an infinitely dense space, a location where the established laws of the universe no longer hold true. So, why is the event horizon of such great importance to astrophysicists? This concept is crucial for defining the limits of our universe and understanding how its most formidable forces function. By examining black holes and their event horizons, scientists gain deeper insights into the very nature of gravity and time, which in turn leads to more profound questions about existence itself. It's a fascinating paradox that, although the event horizon is invisible to us, its influence on the surrounding cosmos is clearly observable. For instance, when a nearby star is torn asunder by a black hole's gravity, we can detect the resulting radiation as matter spirals around the boundary before being consumed. This cosmic spectacle near the event horizon provides one of the key methods for studying these enigmatic objects. The relationship between light and the event horizon raises other compelling questions. If light is unable to escape, what becomes of the information it contains? This puzzle lies at the core of the information paradox, a major area of debate in modern physics that seeks to unite the principles of quantum mechanics and general relativity. Does a black hole truly destroy information, or is there some mechanism by which it can be preserved? Furthermore, the concept of the event horizon encourages us to think about the nature of fate. An object that crosses this line has an unavoidable destiny, which can prompt us to reflect on our own lives and decisions. It serves as a powerful analogy for those moments when we feel we have passed a point of no return, forcing us to consider how we handle our own pivotal experiences. The event horizon is more than just a physical curiosity. It opens a door to philosophical inquiry. What does it really mean to cross an unbreachable boundary? And does doing so signify an irreversible change? These are questions that touch upon the core of human curiosity, relevant both to our understanding of the universe and our own personal lives. Black holes, and specifically their event horizons, also ignite our imagination about humanity's future potential. If we could one day study these phenomena up close, or even travel near them, what incredible discoveries might we uncover? It's conceivable that we could learn to harness gravity in ways currently deemed impossible, making the event horizon a symbol of our unending quest for knowledge. Ultimately, the event horizon stands as a profound mystery, reminding us that there are still fundamental aspects of the universe that lie beyond our comprehension. As we probe these cosmic frontiers, we not only broaden our knowledge of the cosmos, but also deepen our understanding of ourselves. Human curiosity is insatiable. Much like light trapped by a black hole, our questions will forever push forward into the unknown. So when you gaze at the night sky and contemplate the secrets of black holes, remember that the event horizon is far more than a simple boundary. It represents humanity's ceaseless drive to find its place in this immense universe. This exploration is ongoing, and each question we pose brings us incrementally closer to the truths concealed within these dark and captivating voids. Our journey through these cosmic wonders reveals that black holes are more complex than they first appear. For instance, were you aware that beyond the event horizon, some black holes also feature an extraordinary area called the ergosphere? This region is truly one of a kind, with staggering implications for both physics and our understanding of the cosmos. The ergosphere is an area situated just outside the event horizon of a rotating black hole. To understand this, picture a vortex in a body of water. As the water swirls, objects on the surface are pulled into its rotational motion. A comparable phenomenon occurs within the ergosphere, but on an astronomical scale, with the black hole's intense rotation dragging the very fabric of spacetime along with it. This region, the ergosphere, stretches from the event horizon outward for a considerable distance. Within this zone, anything that enters is inescapably caught in the black hole's powerful spin. The gravitational influence here is so potent that even light is forced to follow its rotational current. However, unlike the event horizon, which is a point of no return, the ergosphere offers a degree of flexibility. Remarkably, if an object enters the ergosphere, it has the potential to exit with more energy than it originally possessed. Can you fathom such a possibility? It would be like a runner completing a lap on a track and somehow finishing with greater speed than when they began. This leads to the crucial question: what makes the ergosphere so significant? To truly appreciate the mystery behind a black hole's rotation, you must first explore the fascinating idea of gravity within the spacetime continuum. When a black hole spins, it does more than simply pull matter toward its center. It actively twists the very fabric of space and time around it. This is much like how a spinning object in water generates a whirlpool, drawing everything that gets close into its powerful swirling motion. A rotating black hole, known as a Kerr black hole, produces a kind of gravitational wind that influences anything in its vicinity. So, what becomes of objects that venture near this gravitational vortex? As something approaches a rotating black hole, it is subjected not only to the intense gravitational pull, but also to the powerful influence of its spin. This means that as it draws closer, the object can be deflected sideways by the rotational force. This phenomenon, referred to as the inertial frame-dragging effect, stands as one of the most captivating characteristics of rotating black holes. This effect is responsible for creating a special region known as the ergosphere, an intermediate zone where escape remains a possibility, unlike the point of no return at the event horizon. This region is not just some theoretical curiosity. It carries very real potential applications. Scientists have put forward the idea that we could extract energy directly from the ergosphere. If an object were to navigate close to a spinning black hole, it could theoretically tap into the rotational energy of the black hole itself. This process is analogous to how a windmill converts the movement of air into power. In this scenario, the black hole's rotation acts as the wind. Of course, any object that strays too close to the event horizon is captured forever by the extreme gravity. But within the ergosphere, opportunities remain. The potential to generate energy from such a source is a concept that deeply intrigues scientists, raising the possibility that black holes could one day serve as power sources for humanity. Naturally, this remains hypothetical and would demand an exceptionally advanced grasp of physics. The ergosphere also introduces captivating questions regarding the nature of time and space. In this extreme environment, time itself behaves differently, as the black hole's spin affects not only matter, but also the perception of time in its immediate area. Could it be that time in the ergosphere flows at a different rate than we experience it here on Earth? These are thrilling questions that push us to contemplate relativity and the ways spacetime becomes warped by a black hole's presence. Research into the ergosphere is ongoing, as scientists strive to better comprehend its inner workings. There are theories proposing that this region could be a place where extraordinary quantum phenomena occur. Uniting quantum physics and general relativity, the two pillars of modern physics, within the context of a black hole, represents a monumental scientific challenge. Nevertheless, human curiosity is relentless in its pursuit of answers. Imagine a future where technological leaps allow us to explore a black hole's ergosphere. What might we find? Perhaps we would encounter new kinds of particles, or even forms of life, that have adapted to these incredibly hostile conditions. Space exploration has always challenged us to think beyond the limits of what we know, and the ergosphere is a prime example of how nature can astonish us with its complexity and power. The concept of the ergosphere also reminds us of how truly small we are in the immensity of the universe. We often become absorbed by our everyday problems, but a glance at the cosmos reveals phenomena that far exceed our current understanding. The existence of the ergosphere and its intimate connection to black holes urges us to consider our place in the universe and the very fabric of reality. These cosmic objects are a constant reminder that science has so much left to discover. Every new answer only seems to open the door to a host of new questions, and it is this unceasing curiosity that drives scientists to continue their exploration. Each small discovery can have a tremendous impact on how we comprehend the universe. As our journey of exploration continues, it is exciting to think about how this knowledge could transform our view of the world. Science is advancing rapidly, and with emerging technologies, we might one day have the chance to explore the ergosphere of a black hole. The reality is that we still have much to learn, and this grand adventure is only just starting. Journeying toward a black hole would mean your perception of time would differ radically from that of anyone observing from a secure distance. This fact compels us to ask a crucial question. What are the implications for our grasp of the universe? The interplay between a spinning black hole and spacetime indicates that gravity is more than a simple pulling force. It is an active element that molds reality itself, prompting a re-evaluation of the fundamental nature of both time and space. The study of rotating black holes also provides a unique vantage point for comprehending larger cosmic events, including the formation of galaxies and the development of the universe's large-scale structures. By observing how these cosmic behemoths influence their surroundings, we uncover clues about the universe's past and its potential future. Simultaneously, their existence poses profound questions about the properties of matter and energy, pushing the boundaries of what we consider physically possible with every new discovery. Beyond the scientific implications, we cannot overlook the sheer fascination these cosmic phenomena ignite. The concept of spinning black holes has not only been a focus of astrophysical research, but has also fueled the creativity of writers, artists, and visionaries for decades. These celestial giants serve as a powerful reminder that while we may be anchored to our world, the universe is teeming with wonders and mysteries that are still waiting to be discovered. To explore this further, we must consider what vacuum energy is and how it connects to black holes. To grasp this, you first need to understand a remarkable idea. A vacuum is not merely an absence of substance. In physics, the vacuum is a cauldron of activity, an ocean of potential where virtual particles constantly spring into and out of being. This ceaseless bubbling of transient particles is what we refer to as vacuum energy. So, how does this relate to black holes? With their extraordinary density and a gravitational pull so immense that nothing can escape, these objects produce a singular effect on the space around them. Much like a colossal magnet drawing in everything nearby, a black hole directly influences this vacuum energy, which leads to a tantalizing possibility. Could we harness this power for purposes beyond simply understanding the cosmos? The notion of extracting energy from the vacuum might seem like something out of science fiction, yet scientists have proposed theoretical methods for achieving it. The key to this process lies in the ergosphere, a specific region located just outside a black hole's event horizon. Within this zone, the black hole's rotation distorts spacetime so intensely that it creates an environment from which energy could theoretically be drawn. much like you could use a rapidly spinning surface to propel yourself forward. If we could tap into this power, what would the consequences be? In theory, this energy could fuel interstellar spacecraft, drive forward our most advanced technologies, or even power settlements on other worlds. Yet, this vision is paired with a critical question of safety. Black holes are exceptionally hazardous, and any attempt to interact with one would demand an incredibly cautious and well-planned strategy. Scientists have put forth various concepts for how we might accomplish this, one of which is the Penrose process, a method suggesting we could capture a portion of the energy moving through the ergosphere. It is incredible to consider that we might devise ways to harness a black hole's energy from millions of light-years away. However, our current technology is nowhere near capable of such an undertaking, making it a distant dream for now, though one that scientific progress may one day make real. Reflecting on vacuum energy and its link to black holes also requires us to weigh the philosophical implications. How could the ability to manipulate vacuum energy alter not just our technology, but our very perception of reality? This line of inquiry brings us to a deeper level of questioning, where we confront the ethical dilemmas that would inevitably arise from wielding such powerful cosmic forces. As our exploration continues, we find that the universe presents us with more questions than answers, challenging us to consider if we are truly ready for the possibilities this energy could unlock. Ultimately, as we persist in exploring the mysteries of black holes and their connection to the vacuum, we can imagine a future where the boundless energy of the universe might one day be within our reach. The research into vacuum energy represents an exciting and promising field, reminding us that every question we pose not only advances science, but also deepens our own curiosity and desire for knowledge in this vast and magnificent cosmos. Our quest for this kind of power connects us with the deepest parts of our own curiosity and our drive to comprehend the cosmos, potentially unlocking doors to discoveries we have yet to even imagine. Considering these concepts allows you to envision a future where science and imagination merge, and where the stars are seen not merely as distant lights, but as abundant sources of energy and knowledge. Have you ever considered the possibility of drawing energy directly from a black hole? The notion may sound as if it were lifted from the pages of a science fiction novel, yet it represents a subject that has captivated scientists and theorists for many years. These mysterious and enthralling cosmic objects, black holes, are renowned for more than just their immense gravitational pull. They hold the potential to serve as nearly endless reservoirs of power. To grasp how this could be feasible, you first need to understand the ergosphere, a fascinating region that exists around rotating black holes. Picture a massive vortex in the sea. As you draw nearer, you can feel its pull. The ergosphere is similar, in that while it isn't the point of no return, it's an area completely dominated by the black hole's spin, where spacetime itself is warped in extraordinary ways. It is within this zone that objects can actually siphon energy from the black hole's rotation. But what is the precise mechanism behind this? As a black hole spins, it literally drags the fabric of space and time around with it, in a phenomenon known as frame dragging. If you can visualize the black hole as a colossal spinning top, getting close means you not only encounter the current of its rotation, but could also harness its momentum. Should an object, like a specially designed spacecraft, venture into the ergosphere, it could, theoretically, exploit the black hole's motion to accelerate and gain energy. Of course, achieving this is far from straightforward. One of the most compelling proposals involves using a device sometimes called an energy probe. This hypothetical instrument would be engineered to enter the ergosphere and use the rotational drag to boost its own velocity, much like a figure skater gains speed by extending their arms, and then, potentially, transmit that captured energy back to us. This concept of tapping into the power of black holes is more than just a theoretical exercise. Scientists are actively exploring how this energy might revolutionize space exploration. Imagine interstellar missions fueled not by limited onboard supplies, but by drawing power from a nearby black hole. Such a capability would fundamentally alter our approach to traversing the cosmos. But it prompts a critical question. Could you ever safely get that close? The dangers are, without a doubt, immense. Approaching a black hole presents colossal risks, from the extreme gravitational forces that would rip any conventional spacecraft to shreds, to the intense radiation generated by the process. Despite this, human curiosity has always pushed us to confront the unknown, and if we can engineer the right technology to shield our vessels and astronauts, we could inaugurate a completely new chapter of space exploration. In this theoretical framework, vacuum energy also assumes a vital role. This is the energy inherent in empty space itself, an untapped resource that, when paired with energy from the ergosphere, could create a nearly infinite power system. Could we truly combine the power of black holes with vacuum energy to address our own planet's energy needs? The very thought of using black holes as power plants forces us to ask profound questions about our place in the universe. Are we destined to be passive observers of these cosmic giants, or can we partner with them to forge a new era of energy? Investigating these possibilities isn't just a technological test. It reshapes our entire understanding of what is achievable in space. It's exhilarating to imagine a future with orbital stations powered by a black hole, where science fiction becomes scientific fact, all because we dared to master these cosmic mysteries. Yet, this prospect also forces us to consider if we can truly manage such immense power without unleashing forces beyond our control. Ultimately, extracting energy from an ergosphere is not only a technical hurdle, but also an ethical one. Do we have the right to harness the power of a black hole, or should we leave these cosmic phenomena untouched? The search for these answers will guide us toward a future where our curiosity and our responsibility are intertwined. In the end, the energy of black holes could define not just our capacity for space travel, but also our very understanding of ourselves and our cosmic role. This brings us to the information paradox, one of the most compelling puzzles in all of modern physics. What becomes of information once it tumbles into a black hole? This question has baffled scientists and philosophers for decades, igniting incredible debates that seem fictional but are grounded in the fundamental laws of our universe. To truly appreciate this paradox, you must first be acquainted with what information means in the context of physics. Think of all information as an immense library, where each book contains specific data about the universe, the state of every particle, the history of every star, and even our own stories. When a black hole forms, it is as if a section of that library has been locked away in a vault from which nothing can escape. The central question is, what happens to those books? Are they erased forever, or is there some way to retrieve them? According to quantum theory, the set of rules that governs the universe at the smallest scales, information can never be truly destroyed. This fundamental principle stands in direct conflict with what appears to happen at the edge of a black hole, creating a profound and fascinating contradiction for science to solve. General relativity, the theory that governs gravity and the fabric of spacetime, dictates that once something passes a black hole's event horizon, it is trapped forever. This concept directly clashes with quantum mechanics, leading to a profound crisis in physics known as the information paradox. For a long time, many physicists contended that information is utterly destroyed inside a black hole, an outcome that would shatter a fundamental principle of the universe. This notion was so deeply unsettling that it caused figures like Stephen Hawking to rethink their entire understanding of black holes. Hawking himself, celebrated for his groundbreaking contributions to cosmology, theorized that a process called Hawking radiation could allow black holes to emit particles. In this way, some sliver of information might just be able to escape. Yet, does this truly resolve the mystery of lost information? An alternative view proposes that information isn't destroyed at all, but rather fundamentally transformed. According to this idea, as an object crosses the event horizon, its data is encoded into the radiation that the black hole releases back into the cosmos. Think of it this way. Instead of burning a book, the black hole translates its contents into a complex code that it broadcasts outward. The problem is, this code would be incredibly difficult to decipher, making the retrieval of information as daunting as reading a text in a language you've never encountered. Meanwhile, another group of physicists advocates for the holographic principle, which suggests that information is stored on the black hole's surface. This theory posits that all data falling in is imprinted on the event horizon, almost as if the black hole itself is a three-dimensional projection of a deeper reality. These ongoing debates surrounding the information paradox also force us to confront profound philosophical questions about reality, time, and space. Is the flow of time strictly linear, or could the journey into a black hole reorganize information in a way that makes time travel possible? Although we lack definitive answers, these inquiries push us to examine the limits of what we genuinely know about our universe. The paradox may appear to be an unsolvable riddle, but it also serves as a tremendous opportunity to broaden our scientific horizons. As researchers continue their investigations, the potential for incredible new discoveries grows ever more exciting. It's possible that a future theory will finally unify relativity and quantum mechanics, providing the key to this profound mystery. When you reflect on the information paradox, it's crucial to see that every discovery moves us closer to grasping the universe's true complexity. While the thought of information being irretrievably lost might feel unnerving, it also highlights that science is a continuously evolving journey in pursuit of answers to our deepest questions. Ultimately, the information paradox encourages us to contemplate our own existence. If all information is indeed preserved, what does that imply about us as a species? Could it mean we are intrinsically linked to the vast cosmos and its many unsolved puzzles? The wonder of the universe is filled with such enigmas, and the information paradox is just one of many that await us on our path toward greater understanding. Now, let's turn to wormholes, one of the most thrilling concepts in both astrophysics and science fiction. What if I were to tell you that hidden pathways exist in space, capable of connecting you to entirely different points in the universe? Picture a tunnel that cuts directly through the fabric of spacetime, enabling instantaneous travel between two locations. This is the incredible possibility offered by wormholes, which are also known as Einstein-Rosen bridges after the scientists who first theorized them. To grasp this idea more clearly, consider a map. To travel from one city to another, you would typically follow the road connecting them. But what if you could simply fold the map and bring the two cities into direct contact? This is essentially how a wormhole is thought to function, creating a shortcut across the immense distances of space-time. However, the first major hurdle is that while wormholes are valid mathematical outcomes of general relativity, we have found no concrete evidence that they actually exist in nature. Some scientists theorize that these cosmic tunnels would be incredibly unstable, likely collapsing before anything could pass through them. Others, however, believe that with sufficiently advanced technology, we might one day learn to stabilize them, opening the door to exploring distant worlds in a matter of moments. Beyond interstellar travel, the theory of wormholes introduces fascinating questions about time itself. Could journeying through one allow you to travel into the past, perhaps to witness historical events or even change their course? This possibility, however, introduces complex logical problems, like the famous grandfather paradox, which explores the consequences of altering a pivotal past event. In this discussion, it's worth noting the close theoretical relationship between black holes and wormholes. Some physicists propose that a black hole could act as the entrance to a wormhole, with its exit located somewhere else in the universe, or perhaps in another universe entirely. This concept raises the question: if you could enter a black hole and emerge in a different time and place, would you dare take that risk? Wormholes have consistently been a popular element in science fiction, where films and novels have explored their potential in great detail. These stories present both optimistic and terrifying scenarios of what such travel could entail. Often, the characters in these narratives are forced to confront serious moral and ethical questions about the responsible use of such a powerful technology. Is it wise to delve into the past, or should some things remain untouched? The science underpinning wormholes is remarkably intricate, frequently bordering on pure speculation. A number of scientists propose that we would require exotic matter, a substance with highly unusual properties, to keep a wormhole stable. Yet the question remains, what exactly is exotic matter? It could be something we simply haven't discovered yet, or perhaps it's a material that we will never find. Another compelling area of inquiry is how wormholes might interact with the energy of the vacuum of space. The void is not genuinely empty. It is a roiling sea of quantum fluctuations that could potentially contribute to the creation or stabilization of wormholes. This concept opens a gateway to a reality where the principles of quantum physics and relativity merge and become deeply intertwined, creating a new framework for understanding the universe. Contemplating wormholes also compels us to reconsider the fundamental nature of time itself. Does time flow in a straight line, or could it be more like a pliable surface that we might manipulate if wormholes prove to be real? This possibility suggests that our perception of time as a linear progression might be an illusion, raising profound philosophical questions about our own existence and our role within the cosmos. Ultimately, wormholes represent an exploratory field where science, philosophy, and imagination converge. Although we lack definitive answers regarding their existence or practicality, the mere thought of them inspires us to envision the future of space exploration and even time travel. As scientific knowledge expands, it continually presents us with new wonders, reminding us that what seems impossible today could very well become the reality of tomorrow. So, whenever you gaze up at the star-filled sky, I encourage you to ponder the marvels that might be waiting for us. From enigmatic black holes to fascinating cosmic gateways that could connect us to the farthest reaches of the universe. Investigating wormholes is more than a physical journey through space. It is an intellectual voyage into our comprehension of time, matter, and perhaps reality itself. It makes you wonder what incredible discoveries the future holds. Have you ever considered whether the immense energy radiating from black holes could be harnessed for humanity's benefit? This notion might sound like it was lifted directly from a science fiction film, yet researchers are actively exploring concepts that could transform these cryptic cosmic phenomena into viable power sources. You could think of black holes as colossal vacuums in space, surrounded by an incredible concentration of matter and energy. For a very long time, the prevailing belief was that anything crossing the event horizon of a black hole was lost to the universe forever. However, more recent studies indicate that the reality is far more complex than that. What if it were possible to capture the energy from these spinning cosmic giants? The idea of extracting power from a black hole is captivating, and it is supported by several compelling theories. One of the most intriguing methods for harvesting this energy involves using the ergosphere, which is a region situated just outside the black hole's event horizon. The ergosphere is an area where the fabric of spacetime itself is dragged along by the black hole's intense rotation. Inside this zone, an extraordinary phenomenon can occur. An object nearing the black hole can actually gain energy by tapping into its rotational force. It's as if you could ride a gravitational wave, allowing the object to emerge from the ergosphere with more energy than it initially possessed. To illustrate, if you were to toss a bowling ball toward a rotating black hole, its rotational motion could powerfully accelerate the ball. Consequently, upon its exit, the ball could possess significantly more energy than it had at the start. This concept, which is known as the Penrose process, is founded on the principle that a black hole's rotational energy can be extracted. But could this theory ever be put into practice? While theoretically possible, we are still a very long way from making it a reality. An exciting part of this energy quest is considering how it could be applied. The power drawn from a single black hole could be enough to energize an entire city or even propel starships on journeys between galaxies. Imagine if your home, instead of depending on solar panels or fossil fuels, drew its power from a distant black hole. It may sound like a fantasy, but the physics supporting this idea encourages us to investigate possibilities that currently lie beyond our technological grasp. However, the path forward is far from straightforward. The technology necessary to approach a black hole and safely extract its energy is still in its earliest developmental stages. As our exploration continues, critical questions emerge. How much power could we realistically obtain? Is it safe to operate in such close proximity to a black hole? And most importantly, can this immense energy be reliably controlled and used in a sustainable manner? Extracting energy from black holes is not merely a theoretical exercise. It also forces us to reflect on our fundamental relationship with the universe. If we were to achieve this, it would open entirely new frontiers in both space exploration and our understanding of physics. But what would the broader implications be for humanity? Could it fundamentally alter our perspective on our existence and our place in the cosmos? As scientists press on with their research, it's vital to weigh both the potential rewards and the inherent risks. The energy of black holes could offer a solution to the global energy crisis we currently face, but it simultaneously presents serious ethical dilemmas. Are we truly prepared to wield such a formidable source of power? And could we successfully resist the temptation to use it for destructive purposes? The prospect of harvesting energy from black holes invites us to dream, to peer beyond the limits of our current knowledge, and to contemplate what lies on the scientific horizon. Every new discovery in this field brings us a step closer to solving the universe's greatest mysteries and to better understanding our own role within it. The journey toward harnessing the power of black holes is only just beginning, and the questions we ask today may hold the key to unlocking the scientific and technological doors of tomorrow. When you look up at the stars, have you ever been struck by a sense of your own smallness against the universe's immense backdrop? That feeling deepens when considering black holes, enigmatic phenomena that appear to bend the very rules of physics. the question of how we can be certain they exist isn't straightforward. The answer lies in decades of observation and research that have gradually pulled back the curtain on these cosmic behemoths. First, it's crucial to grasp that you cannot see a black hole directly, as it emits no light of its own. Astronomers instead infer their presence from the powerful effects they have on their cosmic neighborhoods. Imagine seeing leaves swirling in a circle on a calm day. While you can't see the cause, you can deduce that a hidden force is at play. In the same way, scientists identify black holes by observing the peculiar behavior of nearby matter caught in an overwhelming gravitational field. One of the earliest significant advances in this field occurred in 1994 with the study of a star system within the Lyra constellation. Astronomers noticed a star that seemed to be orbiting a completely invisible companion. Through careful calculations, they determined that this hidden object possessed a mass at least 3 times that of our Sun, presenting compelling evidence for the existence of stellar black holes, which are born from the collapse of massive stars. But the universe also contains supermassive black holes, which are found at the heart of most galaxies, including our own Milky Way. There is strong evidence that these colossal entities can have masses millions or even billions of times greater than the Sun. Researchers uncovered their existence by analyzing the light from stars moving in tight, rapid orbits around them, which allowed them to calculate the mass of the unseen object exerting such a powerful pull. A truly historic event took place in 2016 with the first-ever detection of gravitational waves, a ripple in spacetime that was predicted by Albert Einstein's theories. These particular waves originated from the merger of 2 black holes, and their discovery not only marked a pivotal moment in astrophysics, but also gave science an entirely new tool for investigating these cosmic events from afar. Then, in 2018, the Event Horizon Telescope, a global scientific collaboration, achieved another monumental breakthrough by capturing the first-ever image of a supermassive black hole's event horizon in the M87 galaxy. This incredible picture, which essentially shows the shadow of a cosmic giant, was made possible by a method known as very long baseline interferometry, which synchronizes data from telescopes across the planet, proving how science can unite humanity in the quest for knowledge. Scientists have also learned to identify black holes by detecting the X-ray emissions from the material swirling around them. As gas and dust are drawn into a black hole's gravitational grip, the matter heats to unimaginably high temperatures and radiates intense light, which specialized telescopes can observe. In this way, black holes can indirectly become beacons that allow us to probe their fundamental properties. Of course, reaching this point was not without its challenges, as black holes were once a subject of intense controversy and debate in scientific circles. For many years, some researchers were reluctant to accept their existence, because they seemed to violate our fundamental understanding of physics. Yet, as more and more proof was gathered, the scientific community came to embrace these phenomena as an integral part of the cosmos. Technological progress has been pivotal, enabling astronomers to observe black holes across the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength provides a different piece of the puzzle, helping us construct a more detailed and complete portrait of their true nature. The study of black holes is therefore a constantly evolving field, where theoretical ideas and observational data work hand in hand. An especially inspiring aspect of black hole research is the degree of international cooperation it involves. Projects often unite scientists from all over the world, transcending national and disciplinary boundaries in a shared pursuit of understanding the unknown. With every new discovery, however, we find that more questions arise, pushing the frontiers of our knowledge even further. The number of telescopes and space missions dedicated to this research has grown in recent years, from the Chandra X-ray Observatory to the planned Laser Interferometer Space Antenna, or LISA, which will measure gravitational waves. This field is in a state of continuous expansion, with each new instrument acting like a more powerful lens, bringing these both terrifying and fascinating phenomena into sharper focus. For decades, black holes have ignited the imaginations of authors and filmmakers. But what makes them so compelling? Their immense appeal is rooted in their profound mystery and the way they challenge our perception of reality. They have been imagined in countless forms, from the portals to other dimensions seen in movies like Interstellar, to the philosophical quandaries explored in novels like Frank Herbert's The Black Hole. Ultimately, the journey to understand black holes has advanced dramatically from its theoretical origins, and today, a combination of direct observation and global teamwork is beginning to unlock the secrets these cosmic giants hold. So, the next time you find yourself gazing up at the night sky, remember that somewhere in the universe, black holes may represent far more than the end of matter. They might just hold the key to a future of unlimited energy. But how well do you truly grasp their nature and mechanics? Popular culture frequently portrays black holes as ravenous beasts that consume everything in their vicinity. While certainly a powerful image, this depiction is not entirely accurate. In truth, a black hole isn't a predator on the cosmic prowl, but rather an ultimate threshold from which there is no escape, a point where gravity becomes so immense that even light cannot break free. This idea has been explored across countless media, from novels to video games, where black holes serve as narrative devices that propel characters into the great unknown. Among the most compelling questions is whether you could ever journey through one. Many fictional tales enthusiastically embrace this notion, presenting these cosmic phenomena as gateways to other regions of space, or perhaps even to different eras in time. The reality, however, is far more intricate, as science suggests that surviving such a passage is highly improbable, prompting a fascinating question. Can fiction illuminate our understanding of science? Some films have delved into the complex topic of the information paradox associated with black holes. The movie Interstellar, for instance, hints at the possibility that information might be preserved even after crossing the event horizon. This concept has fascinated many, sparking profound questions about the fundamental fabric of reality. What truly becomes of the information that tumbles into a black hole? Does it vanish forever, or is there some way it can be retrieved? This puzzle has motivated both scientists and storytellers to probe the intersection of scientific theory and philosophical inquiry. Television shows have also tackled the subject of black holes, often in unexpected ways. In The Big Bang Theory, they are used as a source of humor, proving that these complex scientific ideas can be presented in an accessible and amusing manner. By using comedy, the series effectively demystifies science, making it more approachable for a broader audience. This strategy helps foster greater interest in astrophysics, which is vitally important in an age where scientific literacy has never been more critical. Visual art offers another impressive lens through which to view black holes. Across mediums from painting to digital animation, their distinctive form and profound mystery have stirred artists to capture the very essence of these phenomena. Depictions of a black hole encircled by its brilliant accretion disk might appear fantastical, yet they accurately reflect the reality of what exists in deep space. These artistic interpretations are not only visually captivating, but also serve to educate viewers about the true nature of black holes. Video games have discovered a boundless well of inspiration in black holes. In titles such as No Man's Sky, you are given the chance to traverse distant galaxies, encountering black holes that function as cosmic portals along your journey. This experience is not only thrilling for players, but also embeds scientific concepts within an interactive and engaging format. By directly engaging with these phenomena in a virtual world, you can cultivate a more intuitive grasp of how black holes operate within the universe. Within the literary world, authors like Stephen Hawking have brilliantly popularized the science of black holes through their writing. They have managed to translate incredibly complex ideas into an accessible style, reaching a much wider readership. This demonstrates that science and literature are not opposing forces, but can instead coexist, mutually enriching one another. A deep curiosity about the cosmos can be ignited by both rigorous scientific inquiry and imaginative storytelling. An intriguing dimension to this topic is how black holes have evolved into powerful symbols of the unknown. In many narratives, they embody our deepest fears and anxieties about what lies beyond the scope of human comprehension. This potent metaphor is often used to examine themes of loss, sacrifice, and the relentless quest for answers. In this way, black holes transcend their physical properties to become a narrative instrument that encourages deep reflection. In recent years, there has been a surge in conferences and documentaries dedicated to black holes. These productions do more than just inform. They inspire future generations of scientists and researchers. By showcasing the sheer beauty and mystery of the universe, they engage individuals who might not otherwise be drawn to science. The combination of spectacular visual effects and clear, concise explanations makes even the most complex concepts understandable. Ultimately, it is crucial to recognize that, while black holes are captivating phenomena, they also instill a sense of humility in the face of the universe's immensity. They remind us that there is still so much to uncover, and that our current knowledge is merely the visible part of an enormous iceberg. The portrayals of these cosmic giants in popular culture entertain us, but they also motivate us to continue exploring and learning. The next time a movie or book you are enjoying features black holes, remember that beyond the fiction lies a real universe of science and wonder waiting to be discovered. Each story and every depiction beckons you to delve deeper into understanding these enigmatic cosmic entities, and perhaps into finding answers about the universe you inhabit. Black holes, therefore, act as a bridge connecting science and imagination, uniting people through a shared curiosity about the great unknown. In the vast expanse of the cosmos, they stand like enigmatic sentinels, inviting us to explore the frontiers of our knowledge. But how are these fascinating phenomena actually studied? The solution involves a range of dedicated missions and advanced telescopes designed to unlock their secrets. Imagine a dedicated team of scientists and astronomers, armed with state-of-the-art technology, working relentlessly to observe these cosmic titans. How is this accomplished? One of the most essential instruments in this endeavor is the Hubble Space Telescope. Since its deployment, it has delivered breathtaking images and crucial data about black holes, enabling researchers to peer deeper into space than ever before. Did you know that Hubble can detect the light produced by matter as it is pulled into a black hole? This material heats up and radiates intensely, providing vital clues about the mass and behavior of these celestial objects. Though Hubble is by no means the only tool on this mission, the Event Horizon Telescope represents a revolutionary project, one created with the specific aim of capturing a black hole's shadow. In 2018, It made history by producing the very first image of the black hole at the core of galaxy M87. This landmark achievement served as a powerful confirmation for many theories regarding the nature of these cosmic objects. But this exploration is far from over. Future observatories, such as the James Webb Space Telescope and the Laser Interferometer Space Antenna, or LISA, promise to unveil even more about these mysterious entities. For example, LISA will be dedicated to detecting gravitational waves from black hole mergers, offering unprecedented insights into how they form and evolve over time. Here on Earth, scientists are also pioneering new frontiers with gravitational wave detectors like LIGO and Virgo. These incredible facilities have enabled us to effectively hear the ripples in spacetime generated by the merging of black holes. Have you ever stopped to think about what these waves represent? They are like echoes from across the cosmos, telling us dramatic stories of cataclysmic collisions between these celestial giants. In addition, missions are being developed to explore the regions surrounding black holes. The European Euclid mission, slated for launch in the near future, intends to map the structure of the universe and achieve a better grasp of dark matter. In the process, it will also provide valuable clues about the profound influence that black holes exert on the formation of galaxies. Meanwhile, astrophysicists employ powerful computer simulations to model the behavior of black holes and their effects on the fabric of spacetime. These simulations function as miniature universes where they can experiment and visualize the interactions of these colossal objects with their surroundings. Did you know that some of these models are so precise they can even predict the appearance of light in the vicinity of a black hole? International collaboration is also a cornerstone in the study of black holes. Scientists from many different nations unite to share their data and combine their resources, which forges a global network of knowledge. This synergy not only deepens our collective understanding, but also significantly accelerates the pace of research. Something that is frequently overlooked is the critical importance of education and public outreach. As more people grow interested in astrophysics, the demand for information about black holes and other cosmic marvels increases. Channels, podcasts, and documentaries help make complex science accessible to everyone, and this shared curiosity serves as a catalyst for future research. As we continue to probe black holes, we learn not only about these perplexing objects, but also about ourselves and our own place in the cosmos. Every new discovery holds the potential to fundamentally alter our comprehension of the universe. Who can say what new horizons will be revealed to us in the coming decade? Did you know that a great number of myths surrounding black holes stem from movies and science fiction novels? The public's fascination with these cosmic mysteries has inspired tales that, while thrilling, frequently distort the scientific reality. Have you ever been swayed by the idea that black holes are like cosmic vacuum cleaners, relentlessly devouring everything in their path? One of the most common misconceptions is that any object venturing near a black hole will inevitably be consumed. If you picture a whirlpool on a lake, you know that if you keep a safe distance, you will not be pulled in. The same principle applies here. An object can maintain a stable orbit around a black hole as long as it does not cross the irresistible gravitational threshold of the event horizon. Another popular notion suggests that black holes are gateways to other universes, a concept that has truly captured the public imagination. This idea proposes that crossing the event horizon might transport you to another reality or even another time. However, this is not supported by our current understanding of physics, and what truly happens once you pass this boundary remains one of science's greatest unsolved puzzles. In the end, the quest to understand black holes is far more than a scientific objective. It is a fundamentally human adventure. From the telescopes that gaze into the cosmos to the missions that push the limits of our knowledge, every step brings us closer to unraveling the secrets of these cosmic giants. As we continue to look to the sky, let us remember that each black hole we study is a doorway to the unknown, and the future promises to be just as exciting as the past. A widespread assumption holds that black holes are inherently dark and therefore invisible. Although it's correct that they emit no light of their own, this doesn't render them entirely undetectable. In fact, astronomers have devised clever techniques to witness their influence on nearby stars and gas clouds. Similar to how a lighthouse pierces the darkness with its beam, a black hole betrays its location through the powerful gravitational effects it has on the space around it. Perhaps one of the most captivating myths suggests black holes might serve as gateways for traveling through time. This concept has been a staple in numerous works of science fiction, but the actual science is considerably more intricate. Our current understanding of black hole physics indicates that while certain solutions to Einstein's equations could permit time travel in theory, there is absolutely no hard evidence that such pathways are either physically accessible or even exist in our universe. Now, let's address the notion that black holes represent an ultimate point of no return. The truth, however, is that they might not be an ending at all, but rather the start of a new cosmic chapter. Material that plunges into a black hole doesn't simply vanish forever. Some theories propose it could eventually re-emerge as radiation through highly complex mechanisms. From this perspective, black holes are less about destruction and more about fundamental transformation. Another compelling misconception is the belief that all black holes are gargantuan in size. While it's true that supermassive black holes located at the centers of galaxies are genuine titans, there also exist much smaller stellar black holes. These are formed from the collapse of individual massive stars and are considerably more widespread than you might imagine. Essentially, the cosmos is populated with black holes of all scales, each with its own unique history. There is also a tendency to view black holes as malevolent cosmic forces. Yet, within the grand theater of the universe, they fulfill a crucial role in cosmic evolution. They serve as the engines that drive the formation of galaxies and are vital for maintaining the balance of matter and energy. So, instead of being cosmic antagonists, they should be seen as essential players in the unfolding story of the universe. Regarding the idea that black holes are forever beyond our reach and impossible to investigate, it's crucial to recognize the rapid pace of scientific progress. With increasingly advanced telescopes and innovative technologies, humanity is steadily closing the gap in our knowledge of these enigmas. Every new finding moves us a step closer to dismantling the myths and unlocking the secrets that black holes conceal. What about the belief that black holes last forever? While they can persist for extraordinarily long durations, they are thought to eventually dissipate through a process called Hawking radiation. This implies that over immense timescales, even these cosmic giants can fade away. This possibility challenges the image of their indestructibility and introduces another layer of complexity to their existence. Ultimately, it's vital to remember that black holes aren't merely isolated celestial oddities. By studying them, we deepen our knowledge of fundamental physics, relativity, and the elemental forces that shape our cosmos. Far from being simple objects of fascination, they are crucial pieces in the intricate puzzle of the universe. Correcting these common myths allows us to develop a richer appreciation for the universe's complexity, turning each misconception into an opportunity to delve deeper and discover the reality behind these captivating phenomena. Black holes truly represent an intellectual challenge and a portal to the wonders of the cosmos, serving as a reminder that our journey of discovery is only just beginning. The physics that governs them is a mesmerizing labyrinth of ideas that beckons us to test the very limits of our comprehension. Consider what occurs when a colossal star depletes its nuclear fuel. The outcome is determined by a battle between gravity and the star's internal pressure. When the outward pressure can no longer counteract the inward pull of gravity, the star collapses upon itself, giving birth to a black hole. But what makes this stellar collapse so extraordinary? To visualize it, think of placing a bowling ball on a trampoline. The fabric of the trampoline stretches and sags under the weight. A massive star is like an incredibly heavy ball. When its fuel runs out, the trampoline warps so severely that it rips open a bottomless pit. This rupture is what we call a black hole, a region in space with a gravitational pull so intense that nothing, not even light itself, can break free. Isn't it mind-bending to consider that light, the very medium that allows us to perceive reality, is powerless against a black hole's gravity? Now, picture a clock. Near a black hole, time behaves differently than it does for us on Earth. If you were observing someone fall toward a black hole, you would see their clock tick progressively slower as they neared the event horizon. For the person falling, time would feel normal, but from your vantage point, it would appear to grind to a halt, prompting us to question what this relativity means for our concepts of past and future. As we venture further into the physics, we learn that gravity isn't simply a force attracting objects, but is actually the curvature of spacetime itself. In the same way the bowling ball bends the trampoline, black holes profoundly warp the very fabric of our universe. This reality forces us to contemplate how gravity's influence extends to everything around us, and what happens to spacetime in the vicinity of such a powerful object. Black holes don't just consume matter. They can also be sources of energy. One of the most fascinating ideas is Hawking radiation, which proposes that a black hole can actually emit particles. Stephen Hawking theorized that due to quantum effects near the event horizon, particle pairs can spontaneously emerge from the vacuum of space. This suggests that even as black holes are famed for devouring everything, they can also slowly radiate energy back into the universe, a concept that heavily involves the principles of quantum physics. The principle of wave-particle duality reveals that, at its most basic level, reality is far more peculiar than you might ever have guessed. It suggests that particles can act as both localized points and spread-out waves, which opens up the chance that information falling into a black hole isn't lost forever. This very possibility leads us directly into the famous information paradox, forcing you to ask a profound question. If a black hole truly destroys information, does that imply our universe is a place where nothing is truly permanent? The tension between general relativity and quantum mechanics represents one of the greatest hurdles in modern physics. Our current models still fall short of providing a single, coherent framework that can explain the quantum behavior of black holes. This ongoing search for a unified theory compels you to wonder what other fundamental truths about our universe are simply waiting to be uncovered. Black holes also force you to confront the very fabric of reality itself. If space and time are not fixed, but are instead flexible, you have to consider what other phenomena might exist that similarly blur the line between what we accept as real and what is merely possible. The physics of black holes propels you into a philosophical exploration where every new finding seems to generate even more questions about our own existence. It is human curiosity that fuels our drive to investigate and comprehend the cosmos. Each new theory and every single discovery brings you another step closer to unlocking the universe's greatest secrets. Through studying the physics of black holes, you learn not just about these enigmatic celestial objects, but also about yourself and your own place within this immense cosmic expanse. Ultimately, black holes are far more than simple astronomical curiosities. They serve as gateways to understanding the fundamental principles that govern our reality. The mission to understand them is what motivates you to keep exploring, to keep questioning, and to continually push the limits of what you know. What new realities might you uncover on this path? And what will they teach you about the nature of space, time, and existence itself? The science behind black holes serves as a powerful reminder of just how little you truly know and how profoundly mysterious the universe you inhabit really is. They represent doorways to deep inquiries about our cosmos and our very being. The presence of a black hole challenges you to completely rethink your understanding of matter, energy, and time, making them not just physical objects, but philosophical concepts that demand reflection. Every time you contemplate a black hole, a certain feeling of unease is bound to surface, prompting you to wonder what might exist beyond its event horizon. This boundary, which signifies the ultimate point of no return, invites you to envision a realm where the physical laws you are familiar with might no longer hold. Could it be that these mysterious objects are actually windows into dimensions you cannot yet perceive? One of the most fascinating questions that emerges is what the concept of time even signifies within the context of a black hole. According to the general theory of relativity, time is not a universal constant, but is warped by powerful gravitational fields. For an observer approaching an event horizon, time could pass in a completely different way compared to someone watching from a safe distance, a fact that makes you reflect on the very nature of time itself. Thinking about these concepts might lead you to question your entire understanding of information and memory. Is information something that is preserved for eternity, or can it be permanently erased from existence? As you delve deeper into these cosmic puzzles, you encounter the notion that black holes could be passages to other universes, as suggested by wormhole theory. This idea, while seemingly torn from science fiction, raises thrilling philosophical questions about reality. The link between black holes and vacuum energy is another deeply captivating area for you to consider. Quantum physics posits that the vacuum of space is not truly empty, but is instead teeming with potential energy. You have to wonder if black holes could offer a method for accessing this energy in ways you don't yet comprehend, a breakthrough that would utterly transform technology and space exploration. Finally, the study of black holes encourages you to contemplate your own place in the universe. Are you just a tiny speck in an endless ocean of stars and cosmic voids, or is there some deeper significance to your existence? The quest for answers is both humbling and exhilarating, as each discovery about black holes only reinforces the endless cycle of curiosity that drives you to continue exploring the fundamental nature of reality. The universe is an incredibly vast and enigmatic place, filled with phenomena that inspire profound awe. When we speak of the unknown, you might wonder what makes black holes so intensely captivating. From their initial discovery to the most recent theories, these cosmic riddles have seized the imagination of scientists and curious minds alike. As we delve into this subject, it's natural to ask what secrets they conceal and what they might reveal about the very fabric of our universe. The concept of a black hole might sound terrifying, yet they function more like dormant monsters in space. While you cannot see them, their influence on their cosmic neighborhoods is immense. Their mere existence pushes the limits of our comprehension of physics, offering a gateway to everything we have yet to grasp. In this era of boundless information, it can be a challenge to accept that some things remain beyond our sight and complete understanding. Remarkably, each new piece of information we uncover about black holes seems to generate even more questions. How can an object possess such extreme density that not even light can break free from its grasp? This is the very core of what they are. Their gravitational force is so overpowering that as you draw nearer, you are caught in an inescapable embrace, a reality that forces us to reconsider our fundamental ideas of time and space. But what is the ultimate meaning of this for us? Do black holes represent an absolute end, or could they perhaps be the start of something entirely new? Scientific knowledge is in a state of constant evolution, and what was once a deep mystery can become common understanding over time. From the foundation of Einstein's theory to the latest experimental findings, our quest to understand black holes leads us to probe the very frontiers of physics. With every new discovery, we inch closer to deciphering the secrets held by these cosmic behemoths. However, our fascination is not confined to the scientific realm alone. Popular culture has also played a significant role, portraying black holes in movies and literature, and thereby stoking our imaginative fires. You have to wonder how these narratives shape our perception of science, and whether they contain a seed of truth that helps us better understand our position in the cosmos. The energy of the vacuum, the perplexing information paradox, and even the potential for passage through wormholes, all of these ideas compel us to interrogate the reality we think we know. What could the existence of black holes truly signify for the future of our technology? It's conceivable that these celestial phenomena hold the key to ushering in a revolutionary new age of space exploration. Black holes also provide a moment for us to reflect on the delicate nature of life itself. If all matter can be consumed by one, what does that imply for us as human beings? Life is transient, making each day we experience a profound journey. In the same way a black hole devours matter, time moves inexorably forward, sweeping us along into an unknown future, a perspective that can deepen our appreciation for every moment. As our study of black holes progresses, it becomes entwined with complex ethical and philosophical questions regarding our duty to safeguard our planet and its future. If we develop the capacity to harness energy from these cosmic events, are we prepared to manage such power with the necessary responsibility? Science provides us with incredible capabilities, but it also burdens us with the obligation to use them wisely, making the link between science and ethics a vital area to explore. Ultimately, black holes are not merely objects of study for astrophysicists. They act as mirrors that reflect our own deep-seated search for meaning within this immense and cryptic universe. They serve as a powerful reminder that while much remains beyond our comprehension, the very act of posing questions and seeking answers is what defines our humanity. Our fascination with these phenomena is what compels us to explore our innate curiosity for knowledge we may never completely possess. In the end, black holes extend an invitation to contemplate not just the cosmos, but our own place within it, challenging our conceptions of time, information, and existence. By investigating these mysteries, we not only push the boundaries of science, but also draw nearer to a more profound understanding of ourselves. So, as you continue to look up at the night sky, I encourage you to see not just stars, but gateways to the unknown, reminding us that curiosity is the essence of our species. Black holes stand as a profound testament to the fact that within our boundless universe, there is always more to learn and explore. It's conceivable that in this grand pursuit of knowledge, we will uncover not only answers to cosmic questions, but also a more complete understanding of ourselves and our true place within the cosmos.